This is Dr. Hester Jiskoot from the University of Lethbridge, and I'm lecturing for geog3710, lecture 5. It's about maps, coordinate and grid systems. The blue marble is the iconic first photograph taken by humans from space that depicted the entire globe in one photograph. Well before that, humans had derived from measurements and observations that the Earth is, first we thought, round or spherical, and later we calculated that the Earth is a geoid. A geoid differs from a sphere in the sense that it's flattened in the vertical. So if you go around the Earth from the North Pole, all around the Earth, around the South Pole, back to the North Pole, the circumference is 40,008 kilometers, whereas if you go around the Earth around the equatorial circumference, it's 40,075 kilometers. Also, if you go through the center of the Earth from pole to pole, it's shorter than if you go from one side of the equator to the other side of the equator. So now we can measure this with great precision using a science called geodesy. In order to indicate where you are on Earth and to map where you are on Earth, we basically have three broad choices. We can do that in a geographic, a projected, or a local coordinate system. A geographic coordinate system basically tells you on the geoid where you are, and usually we indicate that with latitude and longitude. The projected coordinate system is going from that geoid to a flat map sheet, and we have to make choices about projections. So U2M projections, Albers, Lambert projections. And each of those come with certain restrictions because a flat sheet is not your curved Earth surface. And finally, there's local coordinate system that's mostly in grids that indicate on a local map where you are and sometimes who owns the land or where your roads are. Geographic coordinate systems always include a geodetic datum, which is the theoretical or geodetically derived level, which is a set of reference points according to which the real position on Earth is measured relatively to. So we can have the mean sea level, where we can have an elevation above sea level or an elevation below sea level. And there's different types of theoretical systems that you can use, ellipsoid, geoid, etc. as a datum. Now, a really common datum is the WGS84, which is from the World Geodetic Survey 1984. And here, the spheroid is taken as the common datum worldwide, which is approximately mean sea level. So WGS84 is almost identical to a number of other geographic coordinate systems that are used, for example, in North America and in Europe. Geographic coordinate systems also use units of a measure. So this is degrees. So you express geographic location as degrees north, degrees south, degrees east, degrees west. And to derive degrees north and south, it's easy because you can do that relative to the equator, but to do it east and west, you have to assign one meridian as kind of the center according to which we can go east or west. And usually that prime meridian around the world is taken as the Greenwich prime meridian, which is in the UK. Any position on Earth can be indicated by degrees latitude and degrees longitude, which are angular measurements that are measured relative to the center of the Earth, where for the latitude, the plane of the equator is actually given as the reference, and angles are measured either north or south of that plane of the equator. So here you have the position of Pretoria in South Africa, given as an angular measurement relative to the equatorial plane, and this is approximately 26 degrees south. Now, angular measurements for meridians, so for longitude, are given relative to the prime meridian, which is in our case the Greenwich meridian, which goes close to London, and you can actually measure either east of it or west of it. Now, to go for the latitude, you can go all the way 90 degrees up to the North Pole or 90 degrees south to the South Pole. And the lines of latitude are parallel to each other. In terms of degrees longitude, if you go all the way around the Earth, you go 360 degrees. But you can divide that into 180 degrees east and 180 degrees west. So the meridians of longitude, if you actually go from the equator to the North Pole, they converge. So they go from the longest distance between two meridians at the equator to no distance at all at the North Pole. So at the North Pole, you can turn around your own axis and go around the world in all the 365 degrees. Whereas if you had to walk around the equator to do that, you actually walk around a very long distance. So given that the lines of latitude are parallel to each other, if you go from the equator to the poles, the length of 1 degree latitude, so the length of the distance between the parallels of 1 degree latitude, are approximately 111 kilometers. But they're slightly longer at the poles than at the equator, because at the poles, as you know, the Earth is a geoid, so the poles are slightly flattened and therefore it's slightly longer. Now, the length of 1 degree longitude are not approximately the same all over the Earth, because as you remember, the meridians are actually converging at the poles. So at the poles, they're 0 kilometers, because you could pivot 360 degrees around. At the equator, they're exactly the same length as that 1 degree latitude. So to calculate what your distance is between the degrees longitude, you have to know at which latitude you are. So you take the length of 1 degree latitude, and we can take that in general as 111 kilometers. And then you have to know at that latitude, which is usually given in degrees north or south, so anything between 0 and 90 degrees. So you take the cosine of that degrees latitude times the length of 1 degree latitude, so times 111. So at the equator, the cosine of 0 is actually 1. So at the equator, the length of 1 degree latitude and 1 degree longitude are approximately 111 kilometers. If you go to 30 degrees north, the cosine of 30 degrees is 0.87. So you can already see that the degrees longitude will get 0.87 times 111, so shorter than 111. Now, if you go all the way to the North Pole or the South Pole, the cosine of 90 degrees is 0. So 0 times 111 is 0. So this is a handy trick to know if you want to ever, like from a map, calculate a distance somewhere. If you don't do it in a UTM coordinate system, which is generally given as metric, we can actually still calculate the distance in kilometers if you know your latitude. so the distance of 1 degree longitude is dependent on where you are in terms of distance from the equator. So that's all for the geographic coordinate system. Now we come to the projected system, and that is given in any type of coordinate system, but in today's lecture I'll only talk about the UTM coordinate system. The global UTM system is a cylindrical map projection where you can capture almost the entire Earth. A little bit of the North Polar and South Polar regions are chopped off. And each of these parts are indicated as a grid with equal sizes. So this grid system, it covers the Earth between 84 degrees north and 80 degrees south, and it's divided into 60 east-west zones, and each east-west zone is 6 degrees of longitude wide. So 6 times 60 equals 360. The zones are numbered 1 to 60 eastwards, beginning at the 180th meridian. So that's exactly on the opposite side of the prime meridian. So Canada is therefore in zones 7 to 22. So each of these zones is a rectangular 100,000 meter grid system. So that's superimposed onto the zones. So each of the map systems, you first of all have to know which zone you are in, and then you have to know from which direction you start measuring the meters from a certain reference. So here you see Canada with zones 7 to 22 measured relative to the 180 degrees meridian, and each of these zones is 6 degrees longitude wide. So therefore the zone is actually wider at the bottom than at the top, and it converges all the way up. But superimposed onto these zones, we have a 100,000 by 100,000 meter grid systems. And we start counting in terms of position on these UTM maps. We start counting in the southwestern corner, and then we go up in terms of easting, how far east you go, and then northing, how far north you go. So here's an example of how you indicate locations in the UTM coordinate system. You would actually say first which zone you're in, and then you'd actually say how many meters in terms of easting, and then how many meters in terms of northing. So in this particular zone, we can actually say, oh, there's a church somewhere. It is 357,400 meters easting relative to that southwest corner. And then this northing is always relative to the equator. So easting and northing are two metric numbers that then indicate the exact position of that location. And this, in this example, it's somewhere in Ottawa. So for all locations on Earth, we can either in these two examples indicate the location in a geographic or in a projected coordinate system. And in terms of the geographic coordinate system, it would be degrees north or south, and then degrees east or west. So in terms of geographic system, you always start with north or south, so degrees north or south. And then in terms of degrees east or west. Okay. Whereas in the UTM system, we always indicated from the southwest corner, first indicate how far east it is in meters, and then how far north it is in meters. So now I'll give some examples of Canadian grid systems. So from the smaller scale to the larger scale in terms of map scale. So first for the whole of Canada, and then for part of Canada, and then for Alberta. So for the whole of Canada, we use the Canadian National Topographic System, the NTS maps. And the NTS maps actually use the UTM projection. So at the largest scale, the blocks, or basically each map sheet of the NTS systems, they're actually based on the international map of the world at the 1 to 1 million scale. So on that scale, using the UTM system, the blocks are actually numbered in a certain way, where the far eastern end of Canada, they're actually numbered 1 to 4 going up. And you actually continue like just going north along, like not changing the longitude at all. So then the next block system will actually like capture more of the Canadian North. So therefore, like once you actually get to Saskatchewan, Alberta, and BC, you're at numbers 82, 83, 84. So the map sheets of the NTS topographic system, the first number on your map is always this first number that corresponds to that blocks on the international map of the world. So the blocks at the largest grid scale, so the 1 to 1 million scale, as I indicated on the previous slide, are indicated by a number. So here's 83. And here is an example where the number is 13. So they would be the first number in each of the 150,000 maps. So each 150,000 maps has a number and then a letter and then a number again. So that first number is basically the same block number as your 1 to 1 million map. Then each of these main grids is divided into 16 subgrids that are lettered from A to P, from southeast to northeast in a zigzag way, so like this. Okay, so each of these particular map sheets are now 1 to 250,000 map sheets of the NTS system. Each of these 1 to 250,000 map sheets can then be subdivided into 16 numbers, also numbered from southeast to northeast, in a zigzag way again, as you can see here. And so this particular map sheet, 13C9, would be your map sheet 13, C, which is this particular subsection, and then number 9. So here is your map sheet of 1 to 50,000. And 1 to 50,000 is generally the largest scale map that the Canadian NTS system maps for the entirety of Canada. So Lethbridge is situated on the 1 to 50,000 NTS map sheet number 82H10. So this on the left side is the 1 to 250,000 map sheets. And there you can actually see the block of 82H. And that is subdivided into 16 numbers. And then here's your Lethbridge 1 to 50,000 map. So here you see the extent of the 1 to 50,000 NTS map sheet that covers Lethbridge. And at this scale, the topographic detail is good enough that you can actually use it for navigation and even for enough vertical detail. And that vertical detail is given relative to the UTM reference level, so above sea level. And at Lethbridge, we're 925 meters above sea level approximately. So now I'll give two examples of Canadian local grid systems. First, at the larger scale, the Dominion Land Survey System. And any land survey system, the ultimate goal is usually to have a land parcel of equal size, give a legal land description so that you can talk about ownership and buying and selling. So the Dominion Land Survey system in Canada, started in 1871, and the purpose was to survey the whole of then Western Canada, Manitoba, Saskatchewan, Alberta, and BC. And they did that in increasing detail in terms of blocks that are always given relative to a prime meridian or a meridian that is determined as the starting line. So each of these meridians is the starting line, which is also called the range line. And in first instance, all these parcels were built up as 6 by 6 mile parcels. Sorry, that is not really square. And you can actually indicate it as a range, which is like along that meridian of longitude. So the range is actually going north. And then the township, which is then for each township, it would be a block of 6 by 6 miles going west of that particular meridian. So each of these 6 by 6 mile blocks is called a township, and each township can then be subdivided into sections. And each of these sections, so there's 6 sections along the township line and 6 sections along the range line. And then each of these sections can be subdivided into quarter sections. And quarter sections are subdivided according to the cardinal, like northeast, northwest, southeast, southwest part of the section. So these quarter sections are called also the cardinal subdivision, but ultimately you have the finest subdivision is the legal subdivision, where each of the quarter sections can actually then be subdivided into subquarters. So unlike the NTS system, you don't have like a number and then a letter and then a number, but basically you start always saying which meridian you're at. Then you have a number for the range, so that's how many like of these 6 mile blocks you go up along that particular meridian. And then it's the township number, which is basically like how many like 6 mile blocks are you away towards the west from that particular meridian. And then within that township block, which number of section and which number of legal subdivision do you have? Now you run into a problem if you're trying to superimpose a regular grid of 6 by 6 mile blocks onto meridians of longitude that are converging towards the north. Remember where on slide 10 I explained that the distance between 1 degree longitude is dependent on the latitude at which you are. So in terms of the median land survey system, we are here at 49 degrees north, the 49th parallel, and here we're at 60 degrees north. So the distance between 1 degree longitude at 49 degrees north is 72.8 kilometers, but the distance between 1 degree longitude at 60 degree north is only 55 kilometers. So because of this, the north edge of every township is actually shorter than the south edge of the township. So if you then move to the second township and you make that 6 miles again, you have a misalignment of these townships. So therefore, that misalignment needed to be corrected. And from south to north, we basically have baselines where each of these 6 by 6 blocks start 6 mile blocks start exactly like at the meridian, and in between you have the correction lines. So there's a jog, which we call a jog. Here you can actually see there's a little, it looks like a misalignment, but this kind of alignment towards the left is given as a correction, so that the alignment of that first parcel of the township is still aligned with the edge to the particular meridian. So that's along that correction line. So on the prairies where the roads are really straight, you really notice, because the roads are often on the edges of the townships, and you really noticed these jogs when you actually drive on a north to south road, and suddenly you have to go left right again. So the Dominion land survey system is in fact a very colonial mechanism of land appropriation that allotted land to homesteaders and school for their kids and the Hudson Bay Company and the railroad. So each township has 36 sections. So a township is 6 by 6 miles. So each section is 1 by 1 mile. And for each township, there was a particular distribution towards either homesteaders, schools, the Hudson's Bay Company, and the railroad. So this was the same all over Western Canada and done by the Dominion system. And in fact, it was to have the land settled. And even though the land wasn't really owned properly before, the First Nations actually used the land. The Canadian colonizers then actually suddenly owned these pieces of land. So the Hudson Bay Company and the railroad blocks that were allotted were actually allotted in terms of money. So as you can see on this particular map here, if you have a railroad block over here and over here, obviously they don't connect. So it was more of a monetary way to pay the CPR, Canadian Pacific Rail, than to actually say, okay, you have to build your railway here. So the best sections here were, in terms of agriculture, were given to the homesteaders, and the schools had to be distributed kind of almost evenly, so that they were always at walking distance. But the lots that went to the Hudson Bay Company and the railroad were usually kind of the poorest quality of lands. So here we see a zoom in of the index map from 1919, of the index of the townships Manitoba, Saskatchewan, Alberta, and BC. And this particular map shows you the region around Lethbridge. So Lethbridge is around here. And you can actually see that this the township division here was done after Treaty 7, where the then Indian reserves, First Nation reserve. So here's the Blood Reserve, and here's the Piikani Reserve. They were already given to the First Nations, but all the other regions around there were allotted like townships, as in the previous slide that I indicated. So the Alberta Township Survey is actually based on the Dominion Land Survey system. So it's kind of the same principle. The Alberta Township Survey is designated as being west of particular meridians, so the 4th, the 5th, and the 6th, as you also saw on the Dominion, the bigger map. And the township and the section and the quarter section and the legal subdivision system is the same as I indicated before. So this particular township that you see on the map as the red square on the Alberta map can be indicated as section 1 in township 87, range 18, and west 4 meridian. So township maps can be pretty handy because each county's township map shows the ownership within each of a quarter section. So before you do field work, you always have to check out these ownership township maps, and if you have to trespass onto somebody's land or have to traverse to get to a region that is not owned by individuals but is either Crown land or Alberta Energy land, then you always have to ask permission. So here you see a region close to the Milk River Ridge, where we sometimes take students and we drive to the end of the road, and we've arranged for access with the owner of that particular piece of land, and then we can actually walk from the end of the road to the area where it's Alberta owned, and here we don't actually have to ask for permission. Here we have a steep way down to the Milk River, and then we make our way up again. So each land survey system, whether it's national or regional, it's usually a massive fieldwork undertaking, and the Dominion land survey started in the 1870s, so it was pretty low-tech equipment then. But you can actually see in the field where the borders of some of the sections are. So there's different types of monuments. Sometimes it's a stone monument, but nowadays we often have these brass or copper type monuments in pieces of usually stable pieces of rock. So this is a typical British Columbia survey system where you can actually revisit also these survey points to see if there was any movement because of tectonic movement or any other movement. So there's a handy website where you can actually see for each location in Canada the location in the different types of systems. So in the geographic system, in the UTM system, and in the local grid system. So here you have an address in Lethbridge along the Crow's Nest Trail. You see here, you see the township division with the exact legal subdivision location. Then you see the UTM, remember, with the zone 12 here, and the easting and then the northing. Then you see two different notations of the geographic system in decimal degrees here and in degrees, minutes, and seconds. So almost all maps at 1 to 50,000 or larger scale, so 1 to 20,000 or 1 to 10,000, they usually have a geographic and a projected coordinate system, so latitude, longitude, as well as UTM, and sometimes also a local grid indication. And clearly, like, these grid lines often do not actually run parallel, so you have to be very careful if you want to navigate on these and align your compass, that you know that you align your compass to the UTM, like the north-south lines in there. The UTM grid is often better if you want to navigate and like calculate, okay, how far is this location from that location, because the UTM grid is metrically spaced. The latitude and longitude lines are always given in degrees, latitude and longitude, and they run exactly north-south in terms of the geographic north position. And then east-west in exactly east-west position. And clearly they converge towards the north, but the UTM grid is not converging towards the north. So here you see a map of Glacier National Park. It's the US map where we can actually see three of the grid systems superimposed on top of each other.